Hi, this is Ramesh, and I'm going to present about the assignment one uh, problems given in convective heat transfer course. So, the problem one is a straightforward problem. In a laminar flow pipe in a diameter of 2 centimeter, the velocity and temperature profiles are given, and we need to find the bulk mean temperature. So the bulk mean temperature is the average of mean fluid temperatures at the inlet and exit of the tube. So we have a equation for the bulk mean temperature as 1 by cross sectional area and integral of 0 to the radius and integrating the temperature profile with the cross sectional area will give us the bulk mean temperature of the fluid inside the tube. So plugging in the values of the temperature profile, this 100 minus 3 into 10 power 6, and and this will give us the temperature bulk mean temperature of this problem. So the it is found that temperature bulk mean temperature for this problem is 75.01 degrees Celsius. So I've coded this integral in MATLAB to verify the answer, and it also gave the same value as 75.01 degrees Celsius. I have also plotted the same for same problem. This orange is line is the temperature profile. This we have seen in our theoretical value as well. This is the C-shaped curve is the expected one for the temperature profile, and we can intuitively see that the minimum temperature is around 45, and the maximum temperature is 100. It can also be calculated from the temperature profile, and we can intuitively see that the bulk mean temperature is around 75 because it is in the middle. It is the average of temperature between the inlet and outlet temperatures. So this gives the bulk mean temperature to be 75.01. So this is about the problem one. So problem two is also a very straightforward question. Like we have a fully developed flow in a circular tube with uniform heat transfer rate at the wall. So if the mean fluid velocity is tube it is 1 meter per second, we have to find the heat transfer, convective heat transfer coefficient H for different fluids and with a different diameter of the tube. So we'll go one by one. So for the section A, the air is at 80 degrees Celsius and standard atmospheric pressure. So these are the values I have taken these values from reliable sources on the internet. So we calculate the Reynolds number, and it is found to be 1192 from the Sengel's heat transfer and mass transfer book. It is given that the Reynolds number below 10,000 can be taken as laminar flow, and for laminar flows we can straight away take the Nusselt number as 4.36 for the given bound condition, that is a constant heat flux. So the Nusselt from the Nusselt number, we can calculate the heat transfer coefficient to be 5.15 watts per meter square Kelvin. So uh, the for the B subsection, the same problem is given, but the diameter of the tube is increased. So we can see a drop in heat transfer coefficient from 5 to 2 watts per meter square Kelvin. So for section C, the air is at the same temperature, but the pressure is raised. So we can calculate the by linking the Reynolds number from previous subsection. We can calculate the new Reynolds number, and it is found to be 120, and it is also below 10,000. So this for this the heat transfer coefficient is calculated to be 25 watts per meter square Kelvin. And for D subsection, the fluid is changed to hydrogen at 80 degrees Celsius. And these values are taken from the internet. And based on these values, the calculations are carried out. Like I calculate the density, and from this density, I will get the Reynolds number. And for this Reynolds number, I have calculated the heat transfer coefficient, which is coming around 73.5 watts per meter square Kelvin. So for the final section, the water at a mean temperature of 40 degrees Celsius uh, with the 2 mm diameter tube is given. So for this, the Reynolds number is calculated, and so this we can say as the transition flow, since we don't have a particular formula for calculating the parameters at transitioning region. So I have taken it as the laminar flow, and for the laminar flow, the Nusselt number is 4.36 in a circular tube. So based on this diameter and the heat transfer thermal conductivity of the water at 40 degrees Celsius, the heat transfer coefficient is coming around 1374 watts per meter square Kelvin. So for the final section of liquid sodium, I couldn't find the properties in the internet, but I found that the uh, liquid sodium, the sodium metal, melting point is around 97.9 degrees Celsius, but the since the problem states that is 80 degrees Celsius, the sodium liquid, this solid sodium would have not been melted, and it might still be in the solid form. So that is the note of that problem, and this is about the assignment one. Thank you.